Generator every option seemed to end in tragedy, with the fragile balance of exotic forces maintaining the stability of the wormhole thrown into disequilibrium, tearing the ship and its crew to pieces. The only safe option was to wait, and so they waited. Music. 500 years passed before what was left of the ship finally emerged from the open end of the wormhole. It was still intact, but barely functioning. A broken husk after years of exposure to the harsh conditions within the crew was long dead there. Remained still strapped into the command chairs. Finally, the wormhole was shut down. Clearly, they had miscalculated. The predictions of general relativity were evidently not enough. They thought they had solved every corner of the complex intersection of gravity and quantum mechanics, accounted for every possible interaction, but something simply hadn't worked. Humanity looked out at the distant stars and never felt more alone. Wormholes are complicated. They appear in the equations of general relativity, and the idea of them is almost as old as the theory itself. But unfortunately for those test pilots heading to Neptune, relativity is just a machine that tells us how gravity works in various scenarios, regardless of whether or not the universe actually allows those scenarios. And so what would it take to build a wormhole? Which mechanisms allow for wormholes and which forbid them? And would they transport us to the destinations of our dreams across the stars, or to an early death? Since the beginning, history of the universe has had one simple aim: to tell the story of our universe, whilst also celebrating the geniuses who uncovered our world's secrets, but also the organizations where these revelations occurred, like experiments at CERN or science at NASA, without which we would know so much less about the cosmos. That's our passion project. But what would your passion project be? Whether you want to create documentaries, a podcast, a company that sells services, or a brand that sells products, Squarespace can help. Squarespace is super simple to use and easily allows you to build a totally unique online presence for your project, and members-only content in particular is easy to create on Squarespace. Whether that be videos, blogs, online courses, or memberships, you simply upload your content and choose whether it's a one-time fee or a subscription model. You can also fundraise using built-in donation tools, giving you another way to get ambitious projects off the ground. The website design tools, templates, and styling options are also great features, helping you to quickly realize a visually stunning hub for your project, whatever it is. So head to squarespace.com/history of the universe to save 10% off your first purchase of a website or domain using the code history of the universe, and start your passion project today. Black and Whitehole's critics called it confusing, dense, and absurd, but to Edgar Allan Poe it was his greatest work, yet it was 1848, just 1 year before his mysterious death. Having struggled as a professional writer throughout much of his life, his recent success from The Raven had been a welcome financial reprieve, which he took advantage of to compose what he viewed as his masterpiece, what he called the one great purpose in my literary life. Its title was Eureka. The text is expansive, and today little attention is paid to it, especially compared to his much more famous poems, but some statements in its tangled mass still stand out as oddly prescient. For about 2/3 of the way through the text, in the middle of a section where Poe discusses the expanses of interstellar space, he declares almost out of nowhere that space and duration are one. In Poe's eyes, space and time were the same. Working nearly a century later, Albert Einstein had no idea that in some sense he was recapitulating the thoughts of a long-dead New England poet, but that is exactly what he ended up doing. It was 1905, a year which would become known as Einstein's Annus Mirabilis, a year of miracles. In that single year, Einstein published 5 papers, each one with huge implications for our reality, and one of those papers, perhaps his most consequential, concerned the relationship between movement and energy. It's in this paper that Einstein formulated his special theory of relativity, which showed that the measurements of length and time were relative to the observer. But Einstein's former teacher, Hermann Minkowski, thought that he hadn't gone far enough, and so shortly after, Minkowski offered an intuitive geometric formulation of Einstein's work, presenting the universe as a four-dimensional object, unlike Poe's ideas. However, this new space-time did not mean that space and time were identical. Instead, they were different facets of a single unified entity. But Einstein would learn from his teacher once more and quickly adopted this new idea, using it to make one more gigantic leap in human imagination. In 1915, Einstein unleashed into the unsuspecting world a general theory of relativity in the language of general relativity. Space-time isn't static, it responds to the presence of matter and energy, the unified fabric of spacetime bends and warps due to matter's influence. And in return, that bending of spacetime influences the motion of matter. Indeed, years later, famed physicist John Wheeler would sum it all up with the simple phrase, matter tells space how to curve, and space tells matter how to move. And it's happening all around you, and within you right now. Ripples of gravity, known as gravitational waves, constantly slosh over the Earth, created by distant cataclysmic events. As they pass, they deform space. If you were to measure it down to the level of an atomic nucleus, you could feel yourself being gently stretched and squeezed by those passing waves, much like Poe's writings. The theory of general relativity itself is beautiful, haunting, and sometimes complex and confusing. This is because general relativity is more than a simple physical theory of nature. General relativity is a machine. You start with an input, a particular arrangement of matter, then you feed it into the equations of relativity, and out pops an answer, a prediction for how that matter will behave under the influence of its own gravity. But general relativity doesn't tell you whether that arrangement of matter is real or not. It's up to you to decide what is possible and what is impossible. Indeed, relativity is not alone in physics when it comes to this. Newton's law of universal gravitation, which relativity replaced, was similar. You tell Newton what kind of material arrangement you have, and the equations will tell you how that system behaves. If you want realistic answers, you have to provide realistic scenarios. For example, you could in principle figure out the gravitational influence of a solid metal rod 10,000 light-year long. It's up to you to decide if light-year-long solid metal rods exist in the universe. On that matter, Newton will remain silent. But to make matters even more complicated, unlike Newton's laws that preceded it, general relativity is not a simple equation that could be taught in high school. Instead, it's a set of 10 equations in 4 dimensions, all tangled with each other, and all nonlinear. The physics community knew that it was correct and useful, but it was so difficult to wrangle that most physicists preferred instead to work on subatomic and astrophysical problems. Indeed, the pioneering physicist J.J. Thomson once remarked, "I have to confess that no one has succeeded in stating in clear language what the theory of Einstein's really is." Though there was some progress, soon after Einstein developed relativity, Carl Schwarzschild found a solution involving the simplest arrangement of matter possible. While carrying in the trenches of World War I, in this case, Schwarzschild took the machine of relativity and input something resembling the solar system. Out popped a description of the strength of gravity surrounding the sun. While the solution was intended to mimic the solar system, it contained something else, the possibility of a singularity. The idea that if the ball of matter were to be squeezed below a certain limit, then it would just keep collapsing, its own gravitational pull so strong that it becomes a singular point of infinite density surrounded by a one-way membrane and event horizon. And so the machine of relativity had done its job. Now it was up to physicists to figure out whether the result was possible or not, and most scoffed at the idea. Indeed, Einstein himself rejected it. In a 1939 paper, he argued that no object could ever shrink to the degree that gravity would win out over all the other forces. Frozen stars, as they were named at the time, simply could not exist in the universe. But J. Robert Oppenheimer disagreed. Just a few months after Einstein's publication, Oppenheimer was working with his student Hartland Sender. He had just figured out the maximum possible mass of a neutron star, the densest star possible, and he wondered what would happen to those stars if they went over the mass limit. But Oppenheimer and Sender came to the exact opposite conclusion to Einstein. Once you folded in the rest of our knowledge of physics, they found that there was really nothing to stop the infinite gravitational collapse of a massive enough star, and from there the machine of general relativity told you exactly what would happen. Their paper stating clearly, the star thus tends to close itself off from any communication with a distant observer. Only its gravitational field persists. However, the same day that the duo published their paper, Germany invaded Poland. Their work would be forgotten for decades, and Oppenheimer himself would get swept up in the Manhattan Project and the fraud politics that ensued, never to return to astrophysical mysteries. Despite this, as time went on, it would become indisputable black holes were real and possible. But was that all that the machine of relativity predicted, or was there something more? Modern physics, of course, it's perfectly possible for momentum conservation to be wrong or at least inadequate. But after centuries of investigation, it has shown no signs of weakness, no cracks in its ability to explain how the universe behaves, and so exotic matter seems to be a dead end. But Einstein did show us that matter and energy are merely two sides of the same coin. So if exotic matter can't be made and fashioned into a wormhole, perhaps exotic energy could do the trick. And exotic energy found its beginnings in an old-fashioned shootout. It was just after World War II, and the streets of Copenhagen were standing in for the dusty thoroughfares of the Old West. Suit-wearing cowboys wielded mock weapons and entered into simulated duels with each other. One would have the choice to draw their weapon whenever they chose. The other had to wait for the opponent before they could make a move. One such participant was Rick Casimir, a young graduate student who was more interested in particle physics than fake gunfights. And watching over all of this odd experiment, stopwatch and notebook in hand, was none other than Niels Bohr, the godfather of quantum physics. Casimir was in Copenhagen to work on quantum mechanics, but Bohr had diverted from his main interests to briefly indulge a hypothesis he had created, known today as the gunslinger effect. He believed that automatic responses were faster than intentional ones and had wanted to test the idea. Reluctantly or not, Casimir had to take a break from his studies and pretend to be a gunfighter, and so perhaps that image of fellow graduate students staring at each other across a distance, pretend guns ready at the hip, stuck with him as he returned to hard physics, and imagined the tension and forces between two metal plates held a small distance apart. Studying the effects of quantum mechanics under Bohr, his calculations had shown a remarkable property. With nothing between two metal plates at all, they would spontaneously move towards each other, as if willed together by an invisible new force. But this would turn out to be no new force of nature. It was instead an artifact of quantum mechanics. Quantum mechanics does not envision a universe full of particles. Instead, it sees fields that occupy all of space and time. They are everywhere. These fields are full of vibrations constantly fizzling in and out of existence. Sometimes these vibrations take on more substance and travel. This is what we call a particle, but most simply disappear before they can be noticed by the wider cosmos. And there are, in fact, infinitely many vibrations occurring all throughout the expanse of the universe. However, between the plates, those vibrations are restricted. Through careful calculations, Casimir was able to show that the difference in vibrations outside and inside of the plates led to a gentle push, a force that would impel the plates to come together. And since the region inside the plates had less energy than the average energy of the vacuum, it could be said that the Casimir effect, which was named in his honor, is an expression of negative energy. And a sufficient concentration of negative energy can hold open a wormhole, stabilize it, and allow it to be traveled through. Such a wormhole would be a thing of wonder, completely unlike anything else observed in the universe. Its entrance would be a sphere not unlike the event horizon of a black hole, meaning you could enter the wormhole from any direction, but it would be ablaze with light. Not the light of the surrounding stars, but the light from a distant portion of the universe that is filtered through the opposite end. You could wave hello to a friend in the Andromeda Galaxy. You could examine its stellar contents, and you could travel there yourself. Movement through this wormhole would be relatively stress-free, assuming that the tunnel was properly stabilized with an adequate arrangement of negative energy. You would experience no strong tidal distortions, no incredible warpings of gravity. Although your view of the outside universe would be highly distorted due to the unique geometry of the wormhole tunnel, but you would pass through unscathed, skipping tens, hundreds, millions of light years without a hitch. At least in principle. For once again, things are not quite as straightforward as they seem. We have laws of physics like the general theory of relativity, but usually the maths within these laws has much broader scope than just our physical universe. For example, some solutions to relativity are permitted in our universe, like black holes, while others, like white holes, are not. And so, to help navigate this, over the decades physicists have developed a set of rules to guide which solutions are permitted and which are not. These rules are called energy conditions. There are various, like the strong, dominant, and weak conditions, and in general, they tell us how energy can behave. For example, energy cannot travel faster than light, just like matter. Another condition states that local mass cannot be negative. Exotic matter is simply not allowed due to its momentuming implications. Yet another condition says that local gravity must always be attractive. There may be repulsion, as we see with the accelerated expansion of the universe, but that cannot happen at small scales. The Casimir effect violates the weak energy condition, the rule that energy must always be positive. But, of course, this is only true in the hyperlocal space between the plates. If you average out over a larger volume, including the plates and surrounding environment, total energy is positive, and the energy condition is restored. It is an open question in physics if any of these energy conditions can be violated at large scales. They seem to hold true, but again, they are only guesses based on our experience with gravity. It is possible that strange quantum oddities like the Casimir effect could be amplified by a sufficiently advanced civilization. Indeed, quantum theory predicts the existence of numerous, even infinite, wormholes. The same quantum fields that constantly vibrate and fizzle in and out of existence give rise to an invisible sea of particles, which in turn disturb and disrupt spacetime at the tiniest scales. This is called the quantum foam, a roiling sea of broken and unruly spacetime operating at such small scales in time and space that they escape notice. That foam contains countless submicroscopic wormholes, and so perhaps, as Thorne mused in his 1988 paper, an advanced civilization could take one of these ultra-tiny wormholes and pluck them out of the quantum foam, carefully enlarging them to macroscopic proportions. Perhaps they could find a way to violate the energy conditions at large scales, allowing a Casimir-like effect to go from minute distances between plates to span intergalactic lengths. And perhaps that civilization could use that technology to allow a brave crew to travel to distant stars. But a functioning wormhole, as tantalizing as it sounds, is more than a bridge to faraway galaxies. It is also a tunnel into the past. Breaking chronology. You receive an invitation to a party. The location is the University of Cambridge. If you need more precision, the coordinates of the party are at 52 degrees, 12 minutes, 21 seconds north and 0 degrees, 7 minutes, 4.7 seconds east. And the party takes place precisely at 12 noon Universal Time on the 28th of June in the year 2009. There will be champagne, and your host is none other than famed astrophysicist Stephen Hawking. At that precise place, and more importantly, time, Hawking arrived at the room he had reserved. He sipped some of the champagne and waited. And after several hours of nobody showing up, he departed. And then, and only then, after the party had concluded, did he distribute his invitations. It was a party for time travelers. The lack of guests seemed to be reasonable experimental evidence to show that time travel was not possible. After all, who in the distant future would turn down an opportunity to meet Stephen Hawking? But Hawking himself was not totally dissuaded. I'm hoping copies of the invitation in one form or another will survive for many thousands of years. Maybe one day someone living in the future will find the information and use a wormhole time machine to come back to my party, proving that time travel will one day be possible. And so, was he correct? Could wormholes hold the key to time travel? As far as we can observe, time travel into the past is impossible. And yet, once again, the machine of relativity seems to throw a spanner in the works, as its equations permit it. Let's assume that our knowledge of physics advances from its present state and we discover a way to violate the energy conditions and construct a working traversable wormhole held open by exotic matter or negative energy. You build your device and bounce between the stars faster than light. Never locally, of course. You never ever measure yourself moving faster than light in accordance with relativity. And yet, at the same time, you are able to arrive at your destination before the news of your departure reaches it. You then take one end of your wormhole and accelerate it to nearly the speed of light. Indeed, it doesn't matter where you take it. What matters is that it's fast. Due to special relativity, that end of the wormhole experiences time dilation, its clock becoming unsynchronized with the other end. And so, if you travel outside the wormhole back to the other non-accelerated end and travel through, if your journey time outside the wormhole is less than the difference in time between the two ends, you can arrive before you leave. Wormholes aren't just shortcuts in space, they are shortcuts through time. If the universe allows us to build wormholes, it automatically means that it allows us to build time machines. But time travel opens up so many paradoxes that most physicists point to this reason as sufficient evidence that wormholes are impossible. But why? Why can't we travel through time? Consider this example. You have a machine that creates a wormhole. You can turn the wormhole on. You can also turn the wormhole off. So you turn the wormhole on and travel into the past. Then you turn the wormhole off, or you detonate a bomb and destroy the entire wormhole-making machine entirely. But if the wormhole is off or destroyed, how are you able to travel into the past to turn it off? This is just one example of the myriad paradoxes inherent to time travel. And so, anyone who has deeply studied wormholes has been forced to confront the difficulties of time travel and concoct solutions around it. Novikov himself, the father of white holes, created the self-consistency principle. He suggested that perhaps time travel is allowed, but only in certain limited cases where the past remains unchanged. For example, you throw an asteroid towards the entrance of a wormhole, but at the last minute, just before entering, another asteroid comes flying in, knocking yours off course. It still flies into the wormhole, but at a trajectory you did not anticipate. The asteroid travels through the wormhole and emerges out the other end in its own past only to collide with itself just before entering the wormhole. And so, the history of the universe remains consistent with the past unchanged. Some unknown mechanism prevents the past from being altered. But other physicists rejected the idea of time travel altogether. Indeed, in a 1992 paper, Stephen Hawking himself said, "It seems that there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians." Hawking's chronology protection conjecture states flatly that time travel is forbidden. Instead of trying to find a way to allow wormholes, and thus time travel, to exist, we should instead use the information provided that time travel appears to be forbidden as a guide to building an improved theory of quantum gravity. And yet still, that is not quite the end of it. For perhaps wormholes are not tunnels into the past, but bridges to entirely different universes. In the many-worlds interpretation of quantum mechanics, espoused by Hugh Everett, every quantum interaction leads to a branching multiverse. For example, if we perform an experiment that has a 50-50 chance between two outcomes, one universe with one set of views measures one result, while another universe with another set of views measures the other result. This interpretation of quantum mechanics has many flaws, but is not definitively ruled out by any experiment, and it opens up the possibility that wormholes could allow us to travel to the other branches of the infinitely expanding and splitting quantum tree. Following this logic, perhaps there is a universe out there in the many worlds where revelers from the future did arrive at Hawking's party. In their universe, Hawking's party was always a success. In ours, always a failure. Hawking's chronology protection conjecture holds, and time travel is still allowed. And so, the presence of wormholes in the equations of general relativity opens up a whole range of intriguing, tantalizing possibilities. The ability to leapfrog amongst the stars, the capacity to jump into our own pasts. Perhaps wormholes are forbidden by some yet-to-be-known laws of gravity. Perhaps they are allowed but contain hidden flaws and hidden traps. Or perhaps they are just too slow. In 2019, a team of researchers at Harvard University and the Institute for Advanced Study, the same place where Rosen met Einstein nearly a century before, found a way to concoct wormholes without needing exotic energy. But there was just one catch. These wormholes took much longer than expected. They weren't working with a model of gravity applicable to our universe. Instead, they were focused on a special sort of space-time that only has two spatial dimensions and one of time. Surprisingly, this wormhole requires no exotic matter to stabilize it. Gravity itself takes on a repulsive character in the extreme geometries of the wormhole tunnel, which is more than enough to hold it open and allow for passage. But an analysis of that same geometry revealed that such a tunnel could